Now, okay. Okay, hi everyone. Can you hear me well? I hope that can you hear me? I'm asking because sometimes I can hear you very well, and sometimes I have some interference. Maybe my internet connection today is not so good. So I hope everything is fine and I have no connection problem. But in case, I apologize in advance.
Yeah, everything's fine. I'll stand up with a 3-minute warning. Is that okay?
Okay.
All right, brilliant. We cannot hear you. You got muted.
Sorry. Now you hear me?
Yeah, it works now.
Okay. First of all, I present myself. I'm Claudia Di Maio, and I'm a PhD student at the University of Palermo in Italy, and I'm working at the Astronomical Observatory of Palermo. I'm sorry can I be there with you, but I hope there will be other opportunities to meet you soon. I would like to thank the organization for allowing me to follow the workshop and present my work today, even remotely. So, as I say, today I'll show my recent work that is still ongoing about the optimization of the radial velocity extraction in young active fast rotating stars. Let's see what we'll talk about. As the title of this talk suggests, the goal of this project is the optimization of the radial velocities extraction to improve, first of all, our capability of finding new exoplanets candidate, but also improve our knowledge about the stellar activity. I'll show you in the next slide what information we can extract by using our model. But why we want to do that? We will know that the stellar magnetic activity can induce a spurious variation on the radial velocities and can hide or mimic the presence of a planet. And this, of course, is a problem when we want to find new exoplanets, a problem that we want to solve. But how we want to do that? We developed a model for the radial velocity extraction based on the cross-correlation function technique that takes into account the activity level of the star. And in particular, in this presentation, I will show you the recent results obtained applying this model on V830 Tau. So, as we well know, the stellar magnetic activity can manifest themselves with a variety of phenomena, like star spots, plages, faculas, or flares. And also, we know that one of the main techniques used for finding new exoplanets candidate is the Doppler spectroscopy, in which we're looking for tiny periodic Doppler shift caused by the gravitational attraction between star and orbiting planet. Although these two arguments can seem totally different, everyone in this room knows that these arguments are strongly connected. In fact, the intrinsic variability of the host stars is one of the main problems when we try to find and study exoplanets. The intense stellar activity can produce an alteration of the spectral lines. If we look at the GIF on the left, we can see a representation of the deformation of the spectral line due to the presence of a spot on the stellar disk. And how we can see how the bump moves along the line while the spot across the stellar disk. So in this case, we can have a wrong determination of the centroid of the line, so a wrong measurement of the radial velocity. And this is one example of how the variability of the star can induce a spurious variation on the radial velocities and mimic a planetary signal. So it's important to study and model the stellar activity to improve our capability of finding exoplanets. In particular, we focus our study on young stars because we want to understand the mechanisms and the timescale of planet formation and migration. And this is one of the goals of the GAPS project. Since 2012, the GAPS project involves a large part of the Italian community working on exoplanets. And in the first 5 years, the project was based on radial velocity surveys with HARPS-N spectrograph at the TNG and was focused on the search and the characterization of planetary systems around stars with different properties. And when we analyzed HARPS or HARPS-N spectra, we know that today we have two different pipelines used for the radial velocity extraction for this kind of spectra. The DRS pipeline, the data reduction software pipeline, that use the cross-correlation function technique, and the TERRA pipeline. The cross-correlation function is computed from the correlation between the measured spectrum and a weighted binary mask, and is constructed by shifting the mask as a function of the Doppler shift. The binary mask consists on a set of boxcar function centered at the theoretical position of the stellar lines. So the resulting CCF is a function describing somehow a flux-weighted beam profile of the stellar absorption lines. The CCF minimum is obtained when the spectrum perfectly matches the binary mask, and this is the desired radial velocity measurement. And to obtain the radial velocity, the DRS fit the CCF with a Gaussian function to obtain the minimum, of course. The TERRA pipeline, instead, consists in a less square matching of a full spectrum template to the observation, template obtained from the observation with the higher signal-to-noise ratio. Many studies have shown that the method used by the TERRA pipeline for the radial velocity extraction provide a significant improvement in accuracy. For example, if you look at the right figure on the slide, adapted from Damaso and collaborators in 2020, in which we compare the radial velocities time series of V830 Tau obtained with the DRS pipeline in the top panel and with the TERRA pipeline in the bottom panel, we can see that the TERRA pipeline obtained a reduced dispersion in radial velocity for all of the seasons. But let's go to see who is V830 Tau and why this target, it seems perfect, the perfect target to test our model. V830 Tau is a T Tauri star. It's a very active and rotating star. It has a rotational period of 2.7 days and a Vision-I of about 30 kilometers per second. And we will see that this is a fundamental characteristics, the Vision-I, if we want to apply our model. On the right figure on the slide, shows one on the normalized CCF profile of V830 Tau. And as you can see from this example, this star has a deformed CCF profile, characterized by the presence of multiple bumps, highlighted by these arrows. And in case like this, the CCF profiles cannot be fitted by a Gaussian function, like the DRS does. So we have to reject this technique. And so obviously the TERRA pipeline is our best choice, as you see in the comparison of the radial velocity time series performed by Damaso in the previous slide, in which TERRA obtained the best accuracy in radial velocity extraction. But TERRA used a single template obtained from the observation of the target, of course, but in a single template, TERRA takes into account the variability of the star, in particular in target with these characteristics and this high level of activity and variability? I'm not sure that the answer of this question is yes. So our aim was to find a model, a function, that can fit these distorted CCF profiles, taking into account the bumps, supposing that these bumps are due to the presence of a spot on the stellar disk, in order to improve the accuracy of the radial velocity extraction. And of course, to do this, the Vision-I of the star is a fundamental characteristics for the applicability of our model, because we have to resolve the deformation due to the spot on the stellar disk on the CCF, and to do that, we need a broadened CCF profile. So we developed the spot model. For a fast rotating star, we can suppose that the main broadening effect is the rotational broadening that dominates with respect to the other broadening effect that usually affect the spectral lines. And as I said before, we can take the CCF as the representation of the main shape of the lines of the spectrum. So for this reason, I choose to base my model on the rotational profile function, the Gray's formula, that we can see on slide. So we assume that we can describe the main CCF profile with a rotational profile. And to take into account the presence of a spot, I choose to describe the spot with a Gray-like formula, so an equation that we can see as a similar expression with respect to the rotational profile of the full disk, but is defined only on the point of the spot. So if we put all this contribution together in a single expression, we have a function that can fit the CCF, that can include the bumps produced by the spot, like in this figure on slide, in which we show the classical shape of the rotational profile, but in which we can see the notch produced by the spot. Of course, the position of the bumps are correlated to the position of the spot on the stellar disk. So the next step will be to place the spot on the stellar disk. But before that, to complete the spot model, because of the particular shape of the rotational profile and trying to follow the CCF profile on its wings, we decide to convolve this function with a Lorentzian function that can describe the wings of the CCF. So now our model is almost ready. The last step, as I said, is to place the spot on the stellar disk, defining the coordinates of the spot in the plane of the stellar disk. Of course, taking into account the inclination of the spin axis of the star with respect to the line of sight. We applied this model to V830 Tau. We choose this target because it's characterized by deformed CCF profiles in all of the observations that we analyzed. And we suppose that from this target, we can obtain good results, improving the radial velocity accuracy. In particular, due to the complexity of the CCF profile of this target, we trying to apply our model, supposing, first of all, the presence of a single spot in the one-spot model, and then the simultaneous presence of two different spots in the two-spot model. And of course, in some cases, like in this example, the two-spot model allows us to better describe the CCF profile. But to estimate the goodness of the model, we calculate the BIC, the Bayesian information criterion, a criterion for model selection. When fitting models, it's possible to increase the likelihood by adding parameters, but doing so may result in overfitting. So the BIC attempt to resolve this problem by introducing a penalty term for the number of parameters in the model. And in this case, in the case of V830 Tau, for all of the analyzed CCFs, we had a strong evidence in supporting the two-spot model against the one-spot model from the BIC. Here I show you another of the CCF of V830 Tau with its corner plot on the left and the position of the spots obtained using the parameter of the fit on the right. And even in this case, we have two pronounced deformation corresponding to two different spots on the stellar disk. I want to show this figure because I want to highlight the information that we can get from the fit, which does not concern only the extraction of the radial velocity. In fact, from the fit, we can also extract information about the inclination of the stellar spin axis with respect to the line of sight, and also information about the spot, latitude, longitude, and filling factor of the spot. That allow us to study the evolution of the stellar activity or the stellar variability in terms of the coverage of the stellar surface by the spot. I analyzed 146 HARPS-N observation of V830 Tau, spanning 3 years from 2017 to 2020. With the spot model, we obtained the radial velocity time series. In this figure on slide, we compare the radial velocity time series obtained with our model, the filled points, and with the radial velocities obtained with the TERRA pipeline, the empty points. We can see that for all of the seasons, we reduced the radial velocity dispersion with respect to the TERRA radial velocities. So this is the first result that suggests that with our model, we actually improve the accuracy in radial velocity extraction. We also performed a GLS periodogram for both datasets. Here we compare the periodogram performed on the spot model dataset on the left and on the TERRA dataset on the right. From both periodograms, we find a significant peak at the rotational period of the star, highlighted by these red points. And we obtained a lower amplitude from the GLS periodogram performed on spot model dataset. Also, we have significant decrease the root mean square of the residuals, and we remove the trend that we can clearly see on the TERRA phase fold residuals in the bottom right panel on the right figure that almost totally disappear in our spot model phase fold residuals. This result suggests that we removed some contribution modulated with the stellar rotation connected with the activity of the star. To confirm these results, we also perform a recursive pre-whitening for both datasets, trying to understand what is the contribution that we removed. In this slide, I show you the original dataset in the top panel for both figures, for the two different datasets, spot model on the left and TERRA on the right. And from the second panel, we can see the recursive pre-whitening. And it's evident from this figure that just for the first pre-whitening, we totally removed the signal at the second harmonic, highlighted by this second red vertical dashed line from the left. That still is present until the third pre-whitening on the TERRA dataset. So this confirmed the previous results and confirmed that at our model, we removed part of the stellar activity. We also test our detection sensitivity by injecting a planetary signal with the same period of the one supposed by Donati and collaborators in 2017, and then Deniet by Damaso in 2020, changing the amplitude of the injected signal from 68 meters per second, the amplitude supposed by Donati, we can see the corresponding periodogram in the second panel, to an amplitude of about 650 meters per second in the bottom panel. In the first panel, instead, we show the original dataset. And first of all, we can see that there is no planetary signal in both datasets. The planetary period supposed by Donati is highlighted by the gray arrow. And at this frequency, we can see any significant peak. After the injection, the periodogram finds a significant peak with a false alarm probability lower than 1% at the orbital period of the injected planet for an amplitude of about 120 meters per second in our dataset. The same peak instead is significant for the TERRA radial velocities periodogram when we inject the planet with an amplitude of about 650 meters per second. So this test demonstrated that with our method, we can detect the planet with an amplitude of the injected signal significantly lower than that necessary for the identification in the TERRA dataset. So we could be able to find a lower mass planet than the one that we could be able to find from the TERRA dataset. In this case, we are talking about 1 mass of Jupiter against 5.5 mass of Jupiter. As I said before, from the fit, we obtained some information not only on the radial velocities, but only even on the spot. In particular, in this slide, we can see the distribution of the longitude of the two spots. To study the spot properties, we make the assumption that the spot system consists on a bigger spot called spot A, the red point in the plot, and a smaller spot called spot B, the blue point in this plot. In the lower panels, we show the GLS periodogram performed for spot A and spot B respectively. And in the case of spot A, we find a significant peak with a false alarm probability lower than 1% at the rotational period of the star, suggesting, even in this case, that we are actually monitoring something that is modulated with the stellar rotation. Also, in the right panel, we show the projected filling factor of the spots. And first of all, we find a range of values compatible for the most part with the values proposed by Messina and collaborators in 2001 for a star with a rotational period of 2.7 days, like V830 Tau, the period of V830 Tau. Also, even in this case, we perform a GLS periodogram, and we find a significant peak with a false alarm probability lower than 0.1% at the semi-period of the star. So even from this parameter, from the periodogram of the projected filling factor, we can see that we are actually monitoring something modulated with the stellar rotation. And in particular, this result suggests the presence of two spots in both sides of the stellar disk. So in conclusion, we developed new method for the radial velocity extraction in fast rotating star. We applied this model on V830 Tau. Actually, in these days, we are applying this model to other targets to test the applicability of the model as a function of the BNI of the star, for example. But applying this method on V830 Tau, we reduced the root mean square of dataset for each season. We reduced the root mean square of the residuals, and we removed the trend observed in the TERRA phase for residuals. And also, after we reduced the amplitude of the signal found at the rotational period of the star. And also after recursive pre-whitening, we show that we are actually removed the contribution due to the second harmonic of the stellar rotation. So all of these results suggest that we are actually removed part of the signal due to the stellar activity. Also, by injecting a planet on both datasets, we demonstrated that with this model, we improved our detection sensitivity. In particular, by injecting the planet with the same period of the one supposed by Donati, we verified that with our dataset, a significant planetary signal could emerge from a planet with an amplitude of 120 meters per second, while for the TERRA dataset, it will be visible only for amplitude greater than 650 meters per second. And so we improve our detection sensitivity. We actually improve our detection sensitivity. And using the information about the spot obtained from the FIT, we can improve our knowledge about the evolution of the spot. We can study the evolution of the spot to better understand the stellar activity. So that's all. And thanks, everybody, for your attention.
Thanks, Per. Questions. So any questions from the people in the room or online? Luis?
I can see you very well, but okay.
Yeah, thank you for a very nice talk. It's very nice to see that we can actually do something about mitigating the effect of stellar activity for these young stars on the RVs themselves. Do you have any feeling? So let's say you apply this way of extracting the radial velocities for a star where there's a planet, or where we think there's a planet. How do you see any problems in having to first assume a spot model when extracting the RVs, and then later, when let's say you would want to fit those RVs with a GP as well to still take into account the stellar activity signal that's left? Do you see a problem in having to make assumptions about the spots at two different steps, in first when extracting the RVs and then later when modeling them?
Actually, we are not apply the GP on this dataset. We are working on this problem because we don't know if the GP actually, we can apply the GP because to this data actually we don't know if it makes sense to apply the GP because applying our model, we actually removed the stellar activity. So usually we apply the GP to model the activity, but if our model removed the stellar activity, the GP can model anything. So maybe the GP would have nothing to model. In the case in which partially remove the rotation signal, I'm not sure that the residual of this signal can be modeled with the kernel that are usually used, such the quasi-periodical kernel or similar. So we're trying to figure out if GP can actually be applied and which kernel we need to use.
All right, yeah, that makes sense. Thanks.
Thank you. Any other questions? If not, I have a question which is on a slightly different note. You mentioned that in this case, you mainly worry about rotation broadening. My question is, as someone who also worked on extraction, when do you need to actually start worrying about pressure broadening or other stuff? When is the star rotating slowly enough that other things become important?
We are testing the applicability of the model for the Bisenai, and the slowly rotating star that we tested is the DS2 that has a Bisenai of about 50 10 kilometers per second, 12 maybe kilometers per second of Bisenai, and for this target we can apply this model. So this is the lower limit of applicability that we test until today.
Brilliant. Okay. Xavier?
Thanks a lot. Just a question as well. So in this case, you have to do the thing that you have mainly two spots that can produce your effect on the CCF. From what I know, like with two spots, you can mainly fit everything. So it could be that on the star you don't have two spots, but you have 4 or 5 spots, and then basically, so the velocity that you measure, depending on the number of spots you have on the star, will probably change quite a lot. So did you investigate by if you were changing the number of spots on the star, if it was influencing the velocity that you measure at the end or not?
Yes, of course, because we can have more than one or two spots on the CCF, and that the number of spots can change the radial velocities. But if we introduce another spot, we try to use 3 spots. But if we introduce more spots, we risk to overfitting the CCF. So it's not easy to say that we have to improve the number of the spots.
Okay, last question, Suzanne.
It's a follow-up, really. Can you hear me okay? Sorry. It's
not very well.
Maybe I can come closer.
Maybe it's my connection. I apologize.
So I think following up on what Xavier was saying, it would be interesting to see how the radial velocity that you measure changes for your best fit 2-spot model, best fit 3-spot model, even if you worry about overfitting, because there's like, what's the best model in the statistical sense, and then what's the best model in the physical sense, and they are slightly different questions. And in an ideal world, you would average over all the models which are compatible with the data, right? You want to marginalize over the number of spots. Now, obviously, that's not easy to do, but I remember when we were worrying about this in the days of Coro 7, a long time ago. we didn't know how to solve this problem, and so we didn't optimize the fits completely. We just said once the fits at this time we were fitting light curves and radial velocity curves, but we just let the fit run until it reached a certain goodness of fit. And we did this hundreds of times and we averaged the results. So it was a kind of poor person's model averaging. Maybe it's a way to go.
Okay, I understand. I will working on it. This is a great suggestion.
All right, great. Thank you very much. Let's thank Claudia again.
Thank you.